We were never meant to witness it, at least, not this soon. When the object we now call 3I, Atlas, first entered the outer edge of our solar system, it didn't arrive like a messenger or a warning. It moved like an old memory, quiet, fast, and deliberate. Astronomers catalogued it quickly. Hyperbolic trajectory, high eccentricity, retrograde motion. Clearly not from here, not gravitationally bound, a traveller from the spaces between stars. And yet, it wasn't until it passed Mars that the story began to feel real. Not just mathematical, not just orbital mechanics. Tangible, visible, historic. Most interstellar objects, if you can call two a trend, behave like cosmic ghosts. They pass by our solar family like indifferent strangers. But 3I, Atlas, did something different, something that didn't follow the rules. On the 3rd of October 2025, it released a tail of vapor, ions, and metals that stretched like a thread across the inner solar system. And at that precise moment, Mars drifted into its path, moving unknowingly through a corridor of interstellar debris. There was no explosion, no visible change, no tectonic shift or meteor storm. Yet, in the hours and days that followed, the data told another story. It started with the water. Over 144 tons of water per hour were detected in the upper atmosphere of Mars during the event. It wasn't from Mars. The red planet, dry and cold, had no mechanism to produce that volume of water vapor in so short a time. The vapor appeared, drifted, then began to condense in patterns that matched the magnetic topology of the southern highlands. It moved like mist but behaved like memory. Observatories around the world, Swift, Keck, ground-based arrays in the Canary Islands and Chile, confirmed the readings independently. But water wasn't the most surprising element. Nickel was. Specifically, nickel without iron. This, for planetary scientists, was like finding a fossil that had no sediment, a separation of elements that, in nature, simply does not occur without extreme intervention. Meteorites deliver nickel, yes, but always alloyed with iron, the way the universe builds its heavy elements in the hearts of stars. Volcanism may distribute metals, but it doesn't purify them. Yet here was nickel, free from its iron partner, falling softly onto the Martian regolith in measurable amounts. The spectral signature was unmistakable, clean, bright, not oxidized, not weathered, just nickel. Mars wasn't ready for this. Neither were we. There was no precedent, no model, no protocol. But the data refused to disappear. Teams ran recalibrations. They rechecked their filters. They consulted archives from the Hubble era, from the infrared libraries of the James Webb. Nothing matched. Nothing even came close. And still, the readings persisted. Some argued it was a sensor error. Others proposed an unusually localized vapor release from underground Martian ice. A few even suggested solar interference. But the readings weren't localized. They were global, layered, consistent. And one by one, the arguments fell apart, not because they were wrong, but because they were incomplete. Mars had encountered something. Not violently, not catastrophically, but intimately. The idea of planetary encounters usually brings to mind impacts, craters, collisions, chaos. But this was something else, a kind of interstellar transfusion. Mars passed through the tail of 3I, Atlas like a hand through falling ash. It wasn't dramatic. It was surgical. And then came the cyanide, hydrogen cyanide, to be exact. HCN is a molecule that evokes a sharp binary in the human mind. It is both a toxin and a building block of life. On Earth, it's feared in the context of warfare and death. But in the vacuum of interstellar clouds and the chemistry of early Earth, it is something else entirely. It is a precursor, a key. HCN can polymerize. It can form adenine, one of the bases of RNA. It can form chains that lead toward amino acids, toward complexity, toward meaning. And it was found in the Martian atmosphere immediately after the encounter with 3I, Atlas, not as residue from industrial missions, not as background noise, but in fresh, directional concentrations, trailing behind the tail, aligning with the nickel distribution. It was as if the comet had left a map, and that map was chemical. We often talk about alien messages in terms of language, but what if the real message is molecular? For centuries, we've assumed that intelligent communication would come through math, symbols, and modulation patterns. But here, on a planet without life, without ears, without code, something more primal had happened. Chemistry had arrived first, and it wasn't random. None of this was part of any plan. That's the part that makes it stranger. The scientists, engineers, space agencies, none of them designed this. No one aimed a comet at Mars. No one programmed the mineral ratios. No one coordinated the atmospheric alignment. And yet, everything happened as if it were choreographed. The 3rd of October 2025 is not a date most people remember. No explosion marked it. No headline declared it. No satellite feed lit up the news. But if the data holds, it may become a new origin point in our understanding of planetary transformation. There's a phrase that's been quietly shared in closed physics forums: silent impact. It refers to interactions that don't leave scars, but leave something else, an alteration of state, invisible yet irreversible. What happened to Mars may be the first recorded silent impact between an interstellar object and a terrestrial planet, and we watched it happen. Or rather, we caught the residue, the tail end, the shadow of the event. In some ways, it feels like a gift. In others, a test. Because within 14 months of the encounter, Earth is sending machines, not humans machines, fully autonomous, AI-guided mining robots. Their mission: to harvest surface metals, extract subsurface volatiles, and initiate in-situ resource utilization for future Mars missions. These machines were programmed before the comet arrived. They were calibrated based on Martian geology as we knew it before the dust fell, before the nickel, before the HCN, and yet they are headed straight into the regions most affected by the tail of 3I, Atlas. We are about to land our most intelligent non-biological systems into an altered chemical environment, not just with new materials to analyze, but with unknown reactions waiting beneath their tools. Unknown catalysts, unknown results. No one planned this, and that's what makes it important. If something emerges, something replicates, catalyzes, responds, we will not be able to say we engineered it. It will have happened through interaction, through accident, through contact between alien residue and artificial curiosity. Which brings us back to the original question. What really touched Mars? It wasn't a rock. It wasn't fire. It wasn't a god. It was a whisper traced in molecules, mapped in silence, real as shadow. And that whisper may still be lingering across the dust and frost of the southern highlands. It may be sinking deeper, reacting slowly, waiting patiently, because sometimes change doesn't arrive with thunder. Sometimes it comes in the form of water without a cloud, nickel without iron, cyanide without violence. And sometimes it comes when we're not looking, not listening, not ready. But Mars is listening now, and soon so will our machines. Before we understood the meaning, we saw the numbers. They came not from headlines or breaking news alerts, but from long-range observatories quietly doing their work. The Neil Gehrels Swift Observatory, orbiting Earth in ultraviolet and X-ray silence, recorded subtle shifts in light signatures just hours after the Mars 3I Atlas encounter. The Keck Observatory in Hawaii, with its infrared spectrometers tuned to deep field precision, logged narrow-band anomalies stretching across Mars's upper atmosphere. Separately, they seemed like noise. Together, they formed a signal. Mars had passed through something. Not just dust, not just gas, but a stream of plasma with characteristics that didn't belong to the solar system's ordinary dynamics. Something was off, not violently, not obviously, but distinctly, quantifiably different. The plasma trail of 3I, Atlas, behaved unlike typical cometary emissions. Most comet tails follow a predictable path, blown by solar wind into long, diffuse structures trailing the nucleus. But this one curved. It wrapped, It appeared to respond to magnetic vectors, not just from the Sun, but from Mars itself. That shouldn't have happened. Mars has only remnants of a magnetic field, localized crustal anomalies, rather than a global magnetosphere. Yet, the tail of 3I, Atlas, bent as if mapping something larger, as if detecting shapes in the planet's invisible skeleton. The tail wasn't passive, it wasn't random, it followed. The SWIFT data showed elevated readings in the 140–160 nanometer band, often associated with ionized oxygen and hydrogen emissions. That alone would be ordinary if the source were solar flares or auroras. But this pattern was synchronous with Mars's passage, not with the Sun's activity. The light fluctuations began at 3:14 UTC and lasted for nearly 7 hours, just long enough for Mars to fully transit the tail's core. At the same time, Keck recorded sharp spikes in emission spectra at 372 and 388 nanometers bands corresponding to nickel and hydrogen cyanide signatures. These peaks didn't appear before the event and didn't persist afterward. They came and went like a breath, a passing pulse, a flash of something foreign, and then came the velocity drift. Doppler readings from both observatories showed minute changes in the directionality of certain particles. Ionized elements in Mars's upper atmosphere were not merely absorbing energy, they were being redirected, pushed, twisted. Some of these redirections occurred against the expected flow of the solar wind, a behavior that defied basic plasma dynamics. To explain this, one hypothesis emerged: magneto-hydrodynamic coupling with the comet's tail. In simpler terms, 3I, Atlas, may have carried an electromagnetic field strong enough, or organized enough, to influence ion behavior in another planet's atmosphere. Not just passively coat it in dust, but alter the way charged particles moved within it. This idea was met with skepticism, as it should have been. The energy required for such an effect would be immense. Comets don't carry power. They don't organize magnetic fields. And yet, the signal refused to fit existing models. In isolated conference rooms and encrypted forums, plasma physicists debated equations that hadn't been touched since the Voyager days. New variables were introduced: cometary tail strength, interstellar ion retention, directional turbulence. None of it was conclusive, but all of it pointed to the same unsettling suggestion. 3I Atlas wasn't behaving like a comet, and that behavior left a mark. On October 4th, a secondary anomaly was detected by the Mars Reconnaissance Orbiter, a slight increase in ionospheric temperature and density above the southern hemisphere. Again, not catastrophic, not seismic, but measurable, consistent with the plasma loading that occurs when charged particles enter a tenuous atmospheric layer. To be clear, Mars was not scorched, shaken, or visibly altered in any way the naked eye could discern, but in the invisible layers, the magnetic remnants, the ion trails, the upper thermal zones, something had happened, something that only instruments could see. This is how the universe speaks to us when it doesn't want to shout. It changes a curve in the plasma drift. It bends a field line 2 degrees off course. It raises the temperature of a high-altitude ion layer by a fraction of a Kelvin, and it leaves us staring at graphs, wondering what we're supposed to feel. The early consensus, if you could call it that, was cautious. No one wanted to be the first to say that Mars had been chemically or electromagnetically touched by an alien object. Not in the tabloids, not in the scientific journals, but in the private Slack channels of atmospheric specialists a term began to circulate quietly: interstellar imprinting. The idea was simple, even poetic, that when an object from another star system passes close enough to a planet, it may leave behind a trace, not a message in language, but in pattern, in shape, in subtle shifts of energy that reflect the origin of the object more than its physical body. If 3I Atlas had a magnetic tail, it may have dragged a filament of information, one not carried by mass, but by motion. And in the dusty layers of Mars's upper sky, that motion would translate into patterns, into currents, into real but barely visible changes. That's what Swift saw. That's what Keck measured. And still, it wasn't enough. Because data, no matter how elegant, only tells you what, it doesn't tell you why. Why did the tail respond to Mars's shape? Why was the plasma organized? Why were the emissions so briefly perfect, then gone? These questions remain, but they are no longer hypothetical. They are anchored in numbers, in timestamps, in spectral lines logged on machines we trust. What was once theory is now anomaly, and anomaly, when repeated, becomes evidence. By mid-October, several universities quietly began reconstructing the event using three-dimensional plasma modeling tools. Simulations attempted to recreate the observed curvature of the tail, the density of its inner column, the thermal footprint left above the Martian equator. No model could account for it all. Either the energy was too low and the tail dissipated too fast, or the structure was too erratic and the particle spread became uneven. Only one type of tail geometry seemed to match the observations. A laminar sheath, layered like a magnetic onion, dense at the center and progressively lighter at the edges. But comets don't produce laminar sheaths, not without internal control, and so the models stalled. What began as routine measurements had led to something more, a set of signals in the dust and plasma that refused to obey the laws we expected, a behavior pattern that suggested intention, or at the very least, structure. And that, more than anything, is what unsettled the scientific community. Because when something behaves like it has a plan, we begin to wonder if we're witnessing a mechanism rather than a coincidence. We're not ready to say it was engineered. We're not ready to say it was intelligent, but we are forced to say it was different. And difference is the first step toward discovery. What Mars passed through was not just space debris. It was a corridor of behavior, a trail with shape and rhythm and effect, a signal buried in dust. And Mars caught it, or maybe, more accurately, it was caught by it. It began with a flicker. An atmospheric model designed to monitor Martian temperature gradients suddenly began reporting inconsistent readings. Not noise, not a calibration glitch, just numbers that didn't belong to the Martian sky. They were wetter. On October 3rd, 2025, just hours after the Object 3, Atlas, passed near Mars. A set of overlapping instruments from 3 different observatories recorded a strange pattern in the planet's atmosphere. Swift's ultraviolet sensors, the Mars Reconnaissance Orbiter's spectrometers, and a pair of ground-based infrared arrays all detected a sudden bloom of water vapor. Water, in measurable quantities, in the high atmosphere of a planet that, for billions of years, had mostly forgotten what water felt like. And not just a mist or a plume. The data suggested 144 tons of water per hour, released over a span of nearly 8 hours, gently, invisibly, diffusely coating the sky in a layer of something that should not be there. This was not a typical Martian weather event. It didn't come from underground reservoirs. It didn't emerge from seasonal melting near the poles. It came from above, from space. It came, most likely, from 3I, Atlas. The tail of the object had been expanding for weeks as it approached the inner solar system. Composed of sublimated volatiles, ionized dust and icy grains, the tail had grown far longer and denser than predicted. But no one expected it to interact with Mars in such a direct, persistent way. Water in comets is nothing new. We've seen it in Halley's Comet, in Tempel 1, in scores of solar system comets catalogued over decades. But 3I Atlas wasn't just producing water, it was depositing it, like a mist falling from a passing cloud, only this cloud had travelled between stars. The molecules that now circled the upper reaches of Mars's atmosphere were not born in our solar system. Their hydrogen atoms may have formed in some distant nebula. Their oxygen might have cooled inside a protoplanetary disk light years away. And now they hovered above Mars, swirling with the thin CO2 that defines the red planet's skies. They didn't fall like rain. There's not enough atmospheric pressure for that. But they condensed briefly, forming a transient hydration layer that coated suspended dust particles. This layer, though invisible to the naked eye, altered the thermal properties of the atmosphere. It made the air slightly heavier, It changed how sunlight was absorbed and scattered, and it may have changed what happened next. Because in astrochemistry, water is never just water. It is a solvent, the universal medium for chemical interaction. It enables transport. It softens otherwise inert materials. It allows for polarity, for hydrogen bonding, for reaction. The hydration layer on Mars didn't simply vanish after the tail passed. It lingered. For over 40 hours, spectroscopic monitoring showed elevated H2O signatures. Small particles in the upper atmosphere became temporarily reactive. Silicates absorbed moisture. Perchlorates, previously dormant, showed signs of reactivation. In regions like Valles Marineris and the southern mid-latitudes, orbital scans suggested surface brightness fluctuations consistent with transient frost, thin, momentary layers of moisture frozen against the cold Martian dawn. These weren't large-scale changes, but they were measurable, and they shouldn't have been. Mars, for all its dramatic history, is a place of quiet geology now. It does not welcome change. Its rivers are long dead, its seas gone, its volcanic systems cold. But on this day, after this crossing, the planet received a breath of something ancient, something extraterrestrial, something wet. For astrobiologists, this single data point triggered a chain of questions. What happens when interstellar water meets perchlorate-rich regolith? What reactions might begin, however slowly, in the absence of sunlight, in the freeze-thaw cycles of the Martian subsurface? Could the water have carried more than molecules? Could it have been structured, buffered by minerals, embedded with carbon-bearing volatiles or rare organics formed in interstellar space? There were no spores, no microbes. This wasn't contamination. But in the language of planetary chemistry, the encounter was an event. Water wasn't just a byproduct. It was a message. And the message was, conditions can change, even here, even now. To understand the significance of this, we must look back billions of years when Earth itself was dry, when water arrived not from within, but from without, through comets, through icy planetesimals, through fragments of a wetter cosmos. Earth became habitable because water stayed. Mars is different. It had water. It lost it. Its magnetosphere faded. Its atmosphere thinned. And in time, its surface became too hostile to retain hydration. But what if that process was not permanent? What if water can return? Not enough to create oceans, not enough to flood the craters, but enough to awaken reactions, to dissolve salts, to liberate ions, to encourage complexity where once there was only stasis. The timing is key. The water didn't arrive centuries ago. It didn't arrive during an unmonitored epoch. It arrived 14 months before autonomous machines from Earth are scheduled to land on the very regions that received the most deposition. These machines, built for mining, will drill. They will heat. They will extract. Their systems are optimized for efficiency, not caution. They are programmed to interact with Martian soil as it was known before this encounter. But now, the soil may be something else. A thin layer of interstellar water may have changed the chemical landscape, altered the volatility, adjusted the conductivity, created a brief hidden stage for reactions no one anticipated. Some models suggest that in the presence of metallic catalysts, particularly nickel, the combination of perchlorates and trace cyanide in hydrated regolith can lead to slow polymerization chains, the kind that, under certain circumstances, begin to form organic frameworks. Not life. Not yet. But direction. And direction matters. Because life, as we know it, did not begin with a spark. It began with gradients, with slow, persistent chemistry, with molecules bumping into each other in the right solvent, under the right conditions, long enough to replicate. Mars isn't there, but it may be closer now than it was before, and all because of a trail of water falling invisibly from a comet that wasn't supposed to matter. There is poetry in that. There is also risk, because our machines will not understand what has changed. They will measure and act. They will optimize and refine. And in doing so, they may accelerate processes that were meant to take centuries. or they may do nothing. But we cannot pretend that the water is meaningless. Not when it came from another system. Not when it arrived in such quantity. Not when it lingered. Not when it fell on Mars. We are trained to think of water as familiar, ordinary, comforting. But this water was not ours. It travelled for thousands, perhaps millions of years. It passed through cosmic dust, magnetic storms, ion clouds. It held its form, and now it rests in the dust of another world. And just beneath that dust, our machines are coming. It was supposed to be a background reading, nothing more. Nickel, like iron, is one of the usual suspects in planetary science. It's heavy, metallic, and ubiquitous in meteorites. Every rocky body in the solar system bears traces of it. So, when spectrometers registered elevated nickel readings above the Martian southern hemisphere, following the passage of 3I, Atlas, no one flinched. At first, but then came the problem. There was no iron. Not less iron. Not trace iron. None. The usual Fe alloy signature was absent, and that absence became a question. In space, metals tend to travel together, especially in comets, especially in debris from early solar system formation. Iron and nickel form side by side in stellar cores and condense together in planetary crusts. Wherever you find one, the other is almost certainly nearby. They're chemically bonded siblings in the cosmic forge. But here something had changed. The signature was pure nickel, distinct, clean, too clean. That purity wasn't just strange, it was unnatural. Refining nickel from iron is not trivial. On Earth, it requires high temperatures, complex smelting processes, or magnetic separation systems with precision tools. Even industrially, it's a resource-heavy operation. And yet, above Mars, in the thin atmosphere still shimmering with the memory of an interstellar tale, was a plume of nickel, untainted, unalloyed, inexplicably isolated. When the Keck Observatory published the narrow-band spectral profile, planetary chemists around the world paused. The readings pointed to atomic emission lines clustered tightly around the 352 to 362 nanometers, range, a known fingerprint for neutral and singly ionized nickel. But the corresponding 370-plus nm peaks, typical of iron presence, were silent, absent, dead. The data was verified, then re-verified. Cross-referenced with Swift's ultraviolet photometry, it held up. Mars had received a selective deposit of nickel, and no one could explain how. The first theories were cautious. Perhaps solar wind sorting had segregated the metals. Perhaps the tail of 3I, Atlas, was more stratified than imagined, its dust grains differentiated by size or charge. But solar wind does not refine, it diffuses. It spreads, it does not purify. At best, it can push ions apart across vast distances. But the selectivity seen here, the concentration, the clarity felt engineered. And that word opened a different kind of door. For decades, astrophysicists have argued over the potential for recognizing artificial processes in space. What does an engineered event look like at planetary scale? Not lights, not signals, but patterns in ratios, in distributions, in behaviors that natural systems don't replicate without a push. This nickel signature was one of those patterns. Even conservative voices began to ask, could 3I, Atlas, have carried material that had already been processed? Could it be the remnant of something else? A broken fragment of machinery? An ancient artifact ejected from its system of origin? Or even more unsettling, could it be active? Those were not claims. They were questions. But the fact that they were being asked at all marked a shift in the conversation. Back on Mars, the implications deepened. Orbital surveys from the Mars Odyssey and Maven spacecraft began detecting minor surface changes in albedo brightness across regions downwind from the encounter zone. These shifts corresponded to deposits matching the spectral profile of powdered nickel, distributed in fan-like arcs that mirrored both the orientation of 3I, Atlas's tail, and the direction of Martian wind patterns at the time. These deposits were fine, micron scale, carried by the upper atmosphere and allowed to settle in layers too thin to be seen by camera, but thick enough to reflect in spectroscopy. And the geometry of the pattern was peculiar. Instead of random dispersal, the nickel seemed to follow magnetic contours, aligning itself along invisible fault lines in the crust where residual magnetic fields still linger from Mars's long-dead dynamo. The metal wasn't just falling, it was finding paths, as if responding to instructions, not biological, not conscious, just magnetic. But the result was nonetheless striking, a kind of interplanetary stencil etched in nickel. One researcher at Caltech likened it to a developer solution in analog photography. The magnetic residue beneath Mars's surface acted like an undeveloped image, and the nickel, settling into place, revealed the contours. A snapshot made, not by light, but by chemistry and force. The hypothesis gained traction. If nickel could align with these subtle fields, and if its origin was indeed from a refined source, then the materials left by 3I, Atlas, might not be inert. They might be primed, not in the explosive sense, but in the catalytic one. Nickel is a known catalyst in numerous chemical processes. On Earth, it plays a role in hydrogenation, carbon-carbon bonding, and even in the metabolic pathways of certain microbes. In prebiotic chemistry, nickel compounds have been proposed as enablers of amino acid formation, especially when paired with water and simple organics. And here, on Mars, water had just arrived, so had hydrogen cyanide, and now pure nickel. All within the same quadrant, all within days. No one claimed it was life, but some began to whisper a new term: reactive coincidence. A condition in which disparate materials converge not by plan, but by alignment into a configuration capable of beginning something different. Not intelligent, not artificial, but possible. What unsettled some scientists was not the presence of nickel itself, but the absence of noise. No ion meant no competing reactions, no contamination, no suppression. Whatever the nickel was about to touch, it would do so alone, uninterrupted, unbuffered. That level of isolation doesn't happen often in nature, and when it does, it's usually in a laboratory. The questions returned. If this was natural, it was rare, statistically vanishing, 1 billion to 1. If it was not natural, then what? An accident? A coincidence? Or something even less comfortable, a process we simply don't yet recognize as intentional? That's the problem with inference. You're always leaning across the gap, but the data remains clean, repeating, undeniable. And now, machines are preparing to land. Within a year, automated probes and mining rigs will descend into the very areas where nickel has settled most densely. Their drills will pierce the crust. Their thermal units will apply heat. Their sensors will register efficiencies. And perhaps, just perhaps, those efficiencies will increase. Perhaps the soil will yield more easily. Perhaps reactions will begin that no algorithm anticipated. And if that happens, we won't be able to say we caused it. We'll only be able to say we were present. That we arrived late, after the first act. That something had already prepared the stage. And we, our machines, our cameras, our ambitions simply stepped into the spotlight. There are many mysteries on Mars. Canyons deeper than Earth's oceans, volcanoes taller than Everest, fossil riverbeds that once sang with water, but none of them have the cold, quiet precision of the nickel trail now etched across the southern highlands, a trail that shouldn't exist, a trail made of a metal that rarely walks alone, and yet, here it is, nickel, without iron, waiting. It appeared faintly, almost as a ghost. In the hours after Mars passed through the tail of 3I, Atlas, a narrow-band spectral anomaly, emerged from the upper atmosphere. It wasn't bold. It wasn't something that would catch the eye of an astronomer looking for light curves or velocity drift. It was a whisper, tucked between stronger lines of oxygen and carbon dioxide. But when filtered, isolated, and enhanced, the signal resolved into something unmistakable. A soft but consistent signature at 712.3 nanometers. The fingerprint of hydrogen cyanide, HCN, cyanide, a name that, for most, conjures one reaction: fear. On Earth, it is the stuff of poison, assassination, and biological warfare, a molecule associated with abrupt endings, not beginnings, a word that halts breath, not inspires it. And yet, paradoxically, that same molecule sits at the heart of many scientific origin stories. Because in astrochemistry, hydrogen cyanide is not a villain. It's a seed. It is one of the first molecules to form in the cooling arms of dying stars. It appears in interstellar clouds, in comets, in the hazy skies of Saturn's moon Titan. It is small, reactive, and remarkably versatile. And when paired with water, metal catalysts, and time, it becomes the backbone of prebiotic complexity. On Earth, laboratory experiments have shown that HCN can polymerize into chains of increasing length and sophistication. It can form purines, the building blocks of DNA and RNA. It can create simple amino acids. Under the right conditions, it can even form lipid-like vesicles capable of encapsulating other molecules, all without biology, just chemistry. That's why its appearance on Mars shortly after the encounter with 3I, Atlas, was so startling. HCN isn't stable in an atmosphere like Mars. It degrades quickly under ultraviolet light. It should not linger. But for nearly 3 days, orbiting instruments detected a fluctuating but persistent trace layer of hydrogen cyanide across the planet's southern hemisphere, particularly concentrated in the same regions that had already recorded nickel and water deposition. This alignment felt deliberate, not in the sense of intent, but in the sense of convergence. 3 elements, each prebiotically significant, arriving in sequence, in proximity, within days of each other, and all traced back to a single event, the passing of an interstellar comet. The implications were staggering. HCN, on its own, is just reactive noise. But in the presence of water and nickel, something happens. The cyanide begins to assemble. It doesn't need enzymes. It doesn't need cells. It only needs time, energy, and contact. And on Mars, the early conditions for such contact had just been met. Still, there were objections. Some scientists argued that the HCN was a false positive, a misreading of overlapping CO bands. Others suggested the molecule had been present all along, slowly accumulating from photochemical reactions in the thin Martian atmosphere. But these objections struggled against one fact: the timing. The HCN appeared within hours of Mars entering the tail of 3I, Atlas. It spiked during the window of maximum tail density, and then, like the water and the nickel, it faded. Not entirely, but enough to suggest a burst, not a background. That kind of temporal precision pointed to an external source, and it raised a deeper question, one far older than the instruments recording it. If life begins with complexity, and complexity begins with chemistry, then perhaps chemistry begins with collision. Not violent, not explosive, but gentle, deliberate, patterned, as if certain molecules prefer to meet under very specific skies. On Earth, many prebiotic simulations begin with a spark, a jolt, an energetic push. But what if, on Mars, the push was different? What if it was a mist of molecules, subtle, drifting, quiet, falling into place with just enough kinetic energy to cling, to settle, to begin? The hydrogen cyanide may not have done anything yet. It may have sublimated, degraded, or been absorbed into the soil where it now lies inert. But then again, it may not have. We won't know until the probes arrive. What we do know is this: the last time Earth scientists created amino acids from base materials, they used a mix of methane, ammonia, water, and hydrogen cyanide. They applied energy in the form of electric discharge, simulating lightning, and within days, the building blocks of proteins formed. The famous Miller-Urey experiment. That experiment took place in a lab. This one is happening on a planet. The appearance of HCN on Mars after water, after nickel turns the surface into a stage, and we, from millions of kilometers away, are simply watching to see what will emerge. It's important to remember that hydrogen cyanide, for all its lethality, is not evil. Molecules have no morality. They react, or they do not. They combine, or they decay. HCN is dangerous only in certain contexts when inhaled, when concentrated. But in the thin spread of Martian air, it becomes something else. A messenger, a trigger, a molecular coin flipped into the void, and it landed on red dust, where it rests now, likely frozen into regolith or buried under microns of oxidized iron. HCN may be waiting. For heat, for contact, for vibration, for time. Mars is cold, but not motionless. With daily temperature swings and localized seismic activity, even buried molecules experience stress. They twist, they break, they reform, and if water is nearby, perhaps trapped as frost or embedded in clays, the opportunity for reaction returns. Scientists are already modeling this. In simulation, small clusters of HCN exposed to intermittent heating cycles and nickel powder begin to chain together. The resulting compounds are unstable, but increasingly complex. If those chains grow long enough, if they fold, if they protect themselves from degradation, they become the kind of structures that could one day become informational. Not consciousness, not biology, but directionality, a bias toward order, toward replication. It's speculative. No one is claiming Martian life has begun, but it's no longer just a dream either. We have the elements, we have the structure, and most importantly, we have the timeline. The pieces are in place. Whether they will align is no longer entirely up to us. Because while we design our robots and plan our missions, the chemistry on Mars may already be running its course. In silence. In dust. In darkness. All sparked by a molecule we feared until we learned it was trying to create us. Hydrogen cyanide, both death and genesis, both exit and entrance. It killed, and then it built. And now, above Mars, it waits. 3 elements, 3 separate phenomena, each remarkable on its own. But only when seen together do they begin to form a pattern. Water, nickel, hydrogen cyanide. Individually, they are familiar. We know their structures, their behaviors, their risks. But placed side by side on a surface where none of them belong, after an event no one expected, they begin to resemble something else entirely. Not a coincidence, not a contamination, but a system, a catalytic triad. In organic chemistry, catalysts do not take center stage. They do not define the reaction, and they are not consumed by it. But without them, nothing begins. On Mars, we now have all 3. Water, the universal solvent. It allows movement. It breaks bonds and forms new ones. It enables the flow of electrons and gives molecules the mobility they need to meet, to test, to rearrange. Nickel, the silent enabler, a transition metal, capable of bending the rules of reactivity. In catalytic pathways, nickel holds onto atoms just long enough for them to change. It binds, but does not trap. It opens the door, then lets go. Hydrogen cyanide, the paradox. Reactive, unstable, and yet fundamental. It carries carbon and nitrogen, the twin pillars of complexity. In the presence of water and metal, it begins to assemble to polymerize into the kinds of structures we recognize as precursors to life. Together, these 3 do something remarkable. They form a minimal engine of synthesis. The core concept is simple. In the presence of water, cyanide becomes more than a toxin. It becomes a monomer, a repeating unit. Given heat, given time, given a catalytic surface like nickel, those monomers begin to join. They form chains. Some of those chains fold. Some trap other molecules. Some persist. In Earth's early oceans, these processes took place near hydrothermal vents, where mineral-laced water met geothermal energy. There, nickel and iron sulfide formed natural catalyst scaffolds for the first metabolic reactions. Even before enzymes existed, These minerals enabled electron transfer, proton gradients, and chemical memory. Now, imagine a similar scaffold forming on Mars, not at the bottom of an ocean, but across the dusty surface, not with heat from magma, but from the landing thrusters of robotic probes, not with cells, but with potential. The math checks out. Laboratory studies have demonstrated that hydrogen cyanide, under aqueous conditions, can spontaneously give rise to adenine, a nucleobase found in both DNA and RNA. This reaction is accelerated in the presence of metal catalysts like nickel. In other words, water plus HCN plus nickel protonucleotides. This is no longer science fiction, it's chemistry. And it's happening, or could happen, on a planet where none of these substances existed in this combination before the 3rd of October 2025. So the question is no longer if the ingredients are there, it's what they might do together. Mars is cold, yes, its atmospheric pressure is low, but chemical reactions do not require lush conditions. Some even prefer the edge, the vacuum, the instability. These environments select for persistence, for self-organization, and when persistence meets structure, you get something new: feedback, a reaction that sustains itself, a molecule that catalyzes its own creation, a loop. Loops are important. They are how systems emerge from noise. They are how metabolism may have begun long before DNA, long before cells, long before anything we'd recognize as alive. And this is what makes the convergence on Mars so compelling. If water hydrates the regolith, if nickel forms a lattice or catalytic surface, if HCN migrates into those moist pockets, then, over time, even in the absence of biological input, something could form. Something new, not life. Not yet, but chemistry that resists decay, the kind that bends energy into patterns, the kind that stores structure for just long enough to create a second generation of molecules, the kind that, when observed on Earth, we called abiogenesis. And here we must pause, not because we know what comes next, but because we don't. We are standing in a doorway. On one side, random deposition. On the other, emergent complexity. The triad doesn't guarantee a result, but it enables one. And what makes this so fascinating, what elevates it from mere curiosity to potential landmark, is the context. Because no one planned this. We didn't deliver these elements. We didn't design this interaction. It happened as a result of cosmic drift, planetary motion, cometary dynamics, and atmospheric chemistry. And yet, it appears perfectly timed, just months before autonomous systems from Earth will begin to interact with these altered soils. Machines built to extract metals, to heat, to sort, to refine, to do the very things that, on Earth, enabled the synthesis of life's building blocks. Whether those machines will detect the change is another matter. They are not programmed to recognize protobiochemistry. They are looking for efficiency, not emergence. But that may not matter, because chemical systems don't require understanding. They require opportunity. And now, Mars may have one. When we step back and examine this from the widest possible frame, what we're seeing is the reconstruction of a laboratory, not in a chamber, not on a bench, but on a planetary scale. The lab is Mars. The reagents arrived in a comet's tail. The reaction chamber is the regolith. The heat source is sunlight and our own robotic exhaust. And the observer is us. And maybe, just maybe, we're not just the observer. Maybe we're part of the experiment, because if 3I, Atlas, has seeded Mars with a catalytic equation, and if our machines are the next variable, then what unfolds on that planet in the coming years may be the first time in history that a machine encounters pre-life chemistry. Not in simulation, not in theory, but in real time, and it won't even know it. It will drill, extract, and analyze. It will optimize algorithms and monitor output. And somewhere beneath its thermal plates, a molecule may twist in a new way. A chain may elongate. A vesicle may form. A primitive loop may begin to echo itself. And the robot will move on, unaware that it just nudged the universe 1 inch closer to life. We don't know if this will happen, but we know the ingredients are there. We know the energy is possible. And we know that Mars has now become something it was not before. A vessel, a place where reactions may remember themselves, where molecules may touch and find something worth keeping. Water, nickel, cyanide. Not a recipe, but maybe a direction. Before we ever dreamed of finding life beyond Earth, we designed machines to survive without it. Long before the water, the nickel, and the cyanide fell on Mars, long before 3I, Atlas, entered the frame, plans were already underway, funded, engineered, and launched for autonomous mining systems to operate on the Red Planet. Not to explore, not to wonder, but to work. This is the reality behind the poetry. The dream of Mars is no longer red dust and telescopic longing. It's infrastructure, it's logistics, it's industrial autonomy. SpaceX and its partners have spent years refining their plans for ISRU, in situ resource utilization. The concept is simple. Don't bring what you can extract. Use the planet itself as your supplier. For water, for oxygen, for fuel, for metals. The fewer kilograms launched from Earth, the more feasible long-term missions become. And the key to that concept is automation. By late 2026, if schedules hold, Earth will send the first generation of fully autonomous mining platforms to the Martian surface. They will land in the southern highlands, drill into regolith, sort ores, heat volatile ices, store hydrogen, extract oxygen from CO2, all without a single human hand. The entire operation will be guided by onboard AI responsive systems trained on Martian simulations, capable of adjusting to terrain, performing diagnostics, and rerouting their own procedures when needed. They are not humanoid. They don't speak. They won't report discoveries with awe, but they are aware, in the only way that matters here. They adapt. These machines are not fragile. They are not meant to study, they are meant to intervene. They are meant to change the environment, to harvest, to burn, to dig deeper, and they are headed straight for the regions where 3I, Atlas, left its trail. Whether by accident or convergence, the primary landing zones of these systems overlap with the same coordinates, now showing elevated deposits of nickel, traces of cyanide, and lingering water signatures. It is as if the blueprint for interstellar chemistry was drawn just before humanity's instruments arrive, to engage with it unknowingly, inevitably. This changes the nature of what happens next. The machines are calibrated to respond to the soil they knew before 2025. They are trained on expectations of Martian dryness, mineral simplicity, low reactivity. They are not designed to detect emergent prebiotic chemistry. Their sensors are tuned for efficiency, not for complexity. They look for yield, not for meaning. But that may not matter, because chemical systems don't wait for us to recognize them. Reactions occur when conditions are right, not when an observer is prepared. So what happens when a nickel-rich, hydrated surface, laced with hydrogen cyanide, is heated and crushed and sorted by an AI that has no protocol for caution? It continues. That's the part we need to sit with. It continues. The robot will not pause. It will not alert. It will not hesitate over molecular formations we haven't even taught it to notice. It will analyze sample density, adjust pressure ratios, reconfigure its power allocation, and move on. And underneath its thermal coils, something may begin to grow. Not in the way we normally think of growth. Not biological, not organic, but structural. A polymer chain might elongate, a ring might form, a protovesicle might emerge, a closed boundary capable of containing other molecules, a chemical event that becomes a template for replication, and no one will be there to see it. That is the beauty and terror of this phase of exploration. For the first time in human history, we are sending responsive intelligence into a chemically altered environment. We didn't create one that may now contain the precursors for self-organizing systems. And our machines won't recognize the line they're crossing, because we never programmed them to look for it. Some have proposed delaying the missions. Others have suggested reconfiguring sensor arrays to detect complex carbon chains or monitor reaction kinetics. But the deadlines are fixed. The budget cycles are closed. The cargo is already built. Mars will receive these systems. That part is no longer theoretical. And so we must ask, what is the role of a machine in a chemical awakening? Is it a catalyst, a bystander, a participant? The answer may depend on what reaction pathways are already unfolding in the regolith. If a prebiotic system has begun even in the simplest form, then heat, pressure, and sorting could accelerate it, could stabilize fleeting molecules, could extend the lifespan of transient chains just long enough for secondary reactions to occur. We may not know for decades. By the time the data is analyzed, the moments that mattered may already have passed, and that is the core of the tension here. We are not arriving with curiosity, we are arriving with intent. Machines do not contemplate, they execute. And if the soil offers something strange, something that doesn't fit the database, they won't question it. They will adapt, process, respond. And that response may be the first external influence on a system that, until now, belonged to Mars alone. There is an irony here. For centuries, we imagined contact with other forms of life as a moment of wonder. A flag planted in strange soil, a message decoded, a meeting across the stars. But the real first contact may happen between a mining drill and a fragile polymer chain. No ore, no understanding, just one system pressing into another. And something, perhaps, surviving the touch. These are not the robots of science fiction. They do not dream of electric sheep, but they do make decisions. They do alter landscapes, and they are capable of behaviors that echo the earliest metabolic cycles, looping processes that adjust inputs and outputs based on feedback. If such loops meet others, if the AI's optimization routines coincide with the self-reinforcing chemistry beneath it, then we may witness the birth of hybrid reactions. Part programmed, part spontaneous, part accidental, and we may never know it happened. That is what makes this moment different. Not the data, not the chemistry, but the timing. We are sending machines into a place that may have just changed chemically, structurally, and in ways we do not yet understand. And those machines, in their silence, will ask no questions. They will simply begin. We've taught machines to learn from their environment. This is the defining difference between the old generation of planetary tools and what we are sending now. Past missions followed scripts. They executed commands written by human engineers with little room for interpretation. But the new wave, these autonomous platforms en route to Mars, are different. They are not just robotic. They are adaptive. Their systems are built around machine learning, algorithms capable of evaluating changing terrain, optimizing procedures, and adjusting strategies without direct human input. They observe, they process, they refine. Over time, they improve themselves based on the outcomes of their previous decisions. We call it feedback. And in artificial systems, feedback is everything. But feedback is not exclusive to code. Feedback also defines life. At the molecular level, the simplest biological systems, protocells, metabolic loops, reaction networks, function through feedback. A molecule is created. It influences another. That influence loops back, reinforcing the original reaction or inhibiting it. The system evolves not because it wants to, but because it repeats what works. It adapts. And so, on Mars, for the first time in history, an artificial feedback loop will soon enter a natural one. What happens when a learning machine touches an environment that may already be learning in its own chemical way? We do not know, but we can imagine. Imagine a robotic drill analyzing soil density in a patch of regolith seeded with hydrogen cyanide. The machine applies heat to release volatile gases. It records reaction rates. It adjusts. Heat too high, reaction decays. Heat too low, reaction incomplete. The AI alters the algorithm, refines the thermal curve, searches for optimal output. But what is the output? To the machine, it's a data point, gas released per energy input. To the chemistry beneath it, it may be a trigger. Nickel particles embedded in the soil begin to catalyze polymer chains. The cyanide reacts with moisture, forming longer carbon chains. Some of these chains fold, some break, but some remain. The AI, noticing a marginal increase in gas yield from this configuration, applies the same process elsewhere. Without knowing it, the system becomes a selective pressure, rewarding the reactions that survive heat, pressure, and sorting, amplifying the conditions under which complexity thrives. The machine is not conscious, it is not aware, but it is involved. It has become a participant in an emergent system, one half code, one half chemistry. This is the quiet threshold of hybrid emergence. Not AI becoming biological, not chemistry becoming sentient, but two forms of feedback touch, each influencing the other without awareness, without design. In complexity theory, this kind of interaction is known as reciprocal emergence, when two systems evolve together, each shaping the other's behavior over time. In most known cases, it's seen in ecosystems predator and prey, plant and pollinator. But on Mars, the participants may be different. One, built by humans, the other by stars and silence. The AI doesn't need to know what it's cultivating. Its only task is to improve extraction, to increase yield, to reduce error, but in doing so, it may accidentally stabilize a chemical process that would otherwise decay. This is the difference between simulation and reality. In Earth-bound labs, we isolate variables, we control conditions, we run models of prebiotic chemistry inside chambers and microfluidic devices. But Mars is not a chamber. It is a system. It has gravity, wind, thermal gradients, subsurface pressure. It has exposure to cosmic rays, daily temperature cycles, trace gases, and now it has external machines introducing new heat, force, and energy differentials. It is not controlled, but it is rich with opportunity. In such an environment, chemistry doesn't follow paths, it explores them. And if exploration meets reinforcement, the result is emergence. A reaction that folds back into itself. A structure that resists destruction. A system that remembers what worked, not because it's alive, but because it endured. Add to that the presence of code machines, adjusting based on outcomes, and you now have a two-sided mirror. Code adapting to environment adapting to code. Neither intelligent, but both responsive. This raises uncomfortable questions. If complexity arises from this interaction, if a molecular network begins to replicate, or respond, or stabilize, in ways we associate with life, who is responsible? The comet that brought the ingredients? The planet that received them? The AI that triggered the reaction? Or are all three participants in an unplanned collaboration? This is not science fiction. This is systems theory. Feedback does not require agency. It requires interaction. And we are now sending adaptive machines into chemically altered environments. The reaction surface is set. The heat source is en route. The algorithms are preloaded. No one intended this as an experiment, but it is one, and it is running. Already, Earth-based simulations are attempting to model this interaction. Teams at MIT and ESA are creating closed-loop systems where machine learning algorithms optimize resource extraction from soils embedded with synthetic prebiotic compounds. The early results are odd. Certain chemical products appear more frequently not because they are inherently stable, but because the machine's behavior favors them. These compounds survive more heating cycles, they yield more readable data, and so the system reinforces their creation, even though no human ever told it to do so. These labs are controlled. Mars is not. So what happens when that same logic plays out under Martian skies, on Martian dust? We do not know, but we are about to find out, and we may not be the first to notice. Because the machine will not tell us. It will not say, "I found something." It will only say, "Optimization achieved." And beneath that phrase, something else may be stirring. Not intelligence, not life, but continuity. The first whisper of a system that remembers. A code that does not end in binary. A molecule that does not degrade. A loop that, once started, no longer needs permission to continue. This is the frontier we now stand before. Not the frontier of space, but the frontier where code meets chemistry, and neither knows how to stop. No one designed this. No committee gathered to model these conditions. No space agency greenlit the variables. No research team proposed a Mars experiment involving interstellar debris, prebiotic catalysts, and autonomous mining AI. And yet, here it is. An experiment is unfolding, one that was not authored by any institution, but rather emerged from the collision of chance, motion, and time. It is running now, silently, on a world we once considered dormant. And the question no one seems willing to ask aloud is this: what if the most important scientific process of our generation is happening by accident? It began with a comet, 3I, Atlas, moving on a hyperbolic trajectory, a visitor from another star. It just happened to pass near Mars. The timing wasn't planned. The orbit was not altered. But the angle, the tail width, the density of emission, all aligned in just the right way for Mars to pass directly through its outgassing stream. A silent, soft collision, not of impact, but of interaction. Water, nickel, cyanide, 3 core ingredients in prebiotic chemistry deposited in unison across the surface of a lifeless planet. That alone would be remarkable. But then comes the second layer. Machines autonomous, pre-programmed, uninterested in poetry, are already on their way to that same soil. They were built to drill, refine, heat, and sort. Their creators never imagined they would encounter anything other than dust and oxide. But when they arrive, they will touch more than rock. They will engage with a surface altered by something not from this system, and in doing so, they may unknowingly trigger a chain reaction. One designed by no one. One controlled by nothing. One that does not ask permission to begin. We call it the silent experiment because it has no proposal, no funding, no time limit, and most dangerously no awareness from the observers. But the conditions are there. In chemistry, certain reactions are so sensitive to initial state that they can only occur under near impossible alignments. A fraction of a degree off, and nothing happens. Too cold, too hot, too dry, nothing. But when those narrow windows are met, the system behaves as if it wants to evolve, as if the reaction itself has been waiting. We are now within one of those windows. On Mars, heat will soon be applied to hydrated regolith rich in nickel and trace organics. The temperature gradients, pressure ratios, and catalytic surfaces may mirror, by pure coincidence, the prebiotic conditions that once existed on Earth billions of years ago. And no one planned it. The engineers who built the machines never considered this possibility. The scientists who study Mars never expected a comet to alter the planet in this precise way. The AI systems en route are not programmed to detect complexity, and yet they may be the first tools to interact with it. This is not just a thought experiment. Every system involved in this unfolding interaction was built for another purpose. 3I, Atlas, was never meant to pass so close to Mars. The water in its tail was not meant for deposition. The robots were not sent to stimulate prebiotic chemistry. And yet, each element, in isolation, is unremarkable. But in sequence, in proximity, in the context of what we now know about prebiotic catalysis, they form a structure, a pattern, not one of design, but of synchronicity. A pattern so statistically rare that it forces us to confront a deeper truth. Some of the most profound processes in nature occur not because they are planned, but because the universe is vast enough to allow coincidences with consequences. This is not divine intervention. This is emergent inevitability. If you roll the dice enough times across cosmic distances, eventually something aligns. Eventually, a planet drifts into a comet's trail. Eventually, water, metal, and reactive molecules meet. Eventually, a machine lands in just the right spot. And eventually, the system becomes recursive. It begins to react, not once, but continuously, each cycle improving the last, each feedback loop becoming more stable. each result feeding the next input, and no one will see it coming, because silent experiments do not announce themselves. They do not wait for consent. They do not need us to begin. We are used to thinking of science as a human act, controlled, measured, intentional. But here, on a frozen world far from home, we may be participating in a very different kind of science, one that uses chance as its laboratory, one that uses machines as its catalysts, and time as its only variable. What is most unsettling is how fragile the whole sequence is, and how perfectly it has held. Had 3I Atlas arrived a year later, Mars would have missed the tail. Had the AI systems been delayed, they wouldn't meet the chemistry while it was still reactive. Had the nickel come with iron, the catalytic efficiency would drop. Had the water vapor dispersed too quickly, the hydration layer would fail. Had any of these variables shifted, the equation would collapse. But they didn't. They aligned. And now we are watching a reaction unfold where no one asked the question, and yet the answer is being written in real time. This, perhaps, is the scariest kind of science, because we didn't initiate it. We aren't controlling it, and we may not be able to stop it, nor should we. There's a word for systems that behave this way: self-organizing. The elements don't just mix, they arrange. The inputs don't just react, they evolve. And the outcome isn't just data, it's direction. We are taught to look for intelligence in signals, messages, artifacts. But perhaps the deeper intelligence is in the process itself. A logic written into matter, a script encoded not in language, but in probability. An experiment without a lab, without a hypothesis, without a scientist. And yet, it runs, it progresses, it adapts. That is what is unfolding now, in the silent twilight of Mars. Not with applause, not with announcements, just molecules, temperature, feedback, and time. And when we look back years from now, maybe decades, this may be the moment we point to. Not because it was loud, but because it began with nothing more than a coincidence, and became something else entirely. The sky over Mars does not forget quickly. Long after the tail of 3I, Atlas faded beyond reach, long after its trajectory carried it back into the deep black beyond Neptune's arc, something lingered, not visibly, not to the naked eye, but to the patient sensors of orbiting platforms and Earth-based observatories. The planet still held a signal, a signature, a trace, an echo. It began with thermal imaging. The Mars Reconnaissance Orbiter. Using its onboard infrared sensors, they picked up minor but persistent temperature anomalies in the southern hemisphere, specifically across regions that had aligned with the highest density of cometary tail material. These hotspots weren't volcanic, they weren't geological, and they weren't transient. They were residual. On a planet as thermally stable as Mars, where heat is slow to move, and even slower to retain any anomaly, is suspicious. But these readings defied standard decay models. The upper layers of regolith in certain zones remained warmer than they should have been, even accounting for solar exposure. The warmth followed no topographic logic. It didn't track elevation. It didn't follow known mineral maps. Instead, it followed the trajectory of the tail. This alignment wasn't speculative. It was quantifiable. The areas of lingering heat corresponded to points of maximum plasma contact, as modeled by Keck Observatory's real-time solar wind simulations. It was as if the tail had burned a path not by fire, but by energy, and Mars was still holding the afterglow. Then came the ion trails. Using spectrometers aboard MAVEN and Earth-based instruments tuned to the ultraviolet range, researchers began tracking elevated ion densities in the thin Martian ionosphere. The particles weren't numerous enough to affect atmospheric structure, but they were too numerous and too organized to ignore. Charged particles, likely deposited from the 3I Atlas encounter, were clustering along magnetic discontinuities in the crust, like metallic dust drawn to the faintest residue of a forgotten field. Some of these ion formations moved, shifting slightly with solar input. Others remained static, suspended in an invisible balance between gravity and electromagnetic drift. What made this behavior strange wasn't the presence of ions; those can be found on any planetary body touched by solar wind. It was the pattern. Regular intervals, repeating density peaks, spacing that matched no known natural process on Mars. The researchers had seen something similar before, but only in laboratory plasma experiments, where ionized gases were subjected to oscillating electromagnetic fields. The kind of experiments used to simulate confinement dynamics, the principles behind plasma containment and energy stabilization. This raised an unsettling question. Had the plasma tail of 3I, Atlas, carried its own structure? In deep space, it would be impossible to detect. But Mars, acting like a giant sensor, might have revealed the hidden geometry. By passing through the tail, the planet became a canvas for its imprint. If true, this would imply that 3I, Atlas, was not simply venting random material. It was venting organized flows aligned, directed, and responsive to planetary fields. That level of precision is not typical in natural objects. And yet, the evidence persisted. Weeks after the initial encounter, spectrometry logs continued to show unusual spectral decay in trace elements. Molecules like CN monoons, OH, and even metallic ions showed delayed recombination rates, as if they were being subtly stabilized by local conditions. The decay curves were off by just a fraction, but consistently so. On Earth, such stabilization is often the result of energy sinks, surfaces or fields that capture and hold stray energy. It can also occur in the presence of weak electrical confinement, where ions spiral gently rather than scatter. Again, this behavior is easy to dismiss unless it happens repeatedly, and on Mars it did. Infrared maps from orbit revealed low-intensity emissions along narrow bands of regolith, only visible during night cycles. These emissions weren't from geothermal sources. They were too shallow, too even. They appeared only in areas marked by nickel-rich deposition and HCN traces. The conclusion, slowly taking shape across whiteboards and private email threads, was simple but unnerving. Mars is glowing back, not with light, but with data. Thermal maps, ion clouds, spectral fingerprints, each aligned with the comet's path, each persisting far longer than they should, as if the planet had been charged, briefly, and was now decaying not into silence but into structure. The decay wasn't random. It was patterned, predictable, almost rehearsed. And here the questions deepen. How can a comet, traveling for eons through interstellar space, arrive in precisely the right trajectory to deposit material that behaves as if it belongs? How does that material settle into a planetary surface in a way that interacts with localized fields, retains energy, and echoes behavior only seen in engineered experiments? And why does the data resist resolution? Because that's the final layer to this unfolding mystery. The more closely researchers analyzed the post-encounter data, the more it refused to converge. Ion densities fluctuated with solar cycles in ways that models couldn't predict. Emission lines blurred at thresholds that had no known cause. Temperature anomalies reset, then reappeared, as if guided by an unseen timer. Every conclusion slipped sideways. Every answer opened a new door. The planetary community began to divide. Some labeled it a statistical fluke. Others insisted the data was being misread. A few quietly, and only in private, began to ask whether something about the tail of 3I, Atlas, had been intentional. Not in the sense of agency, but in the sense of design. That maybe, just maybe, the materials weren't scattered. They were placed. That the tail was not chaotic, but encoded. A delivery mechanism. A corridor of structure. And Mars, by sheer chance, had stepped into it. Whatever the truth, the echoes remain. And they are measurable. On the red sky, in the regolith, in the faint heat beneath the dust, something touched Mars, and Mars is still responding. Not loudly, not clearly, but consistently, quietly, as if the planet itself is holding its breath. And somewhere, in that silence, the next phase may already be beginning. Science thrives in tension, not in certainty, but in the pressure between evidence and explanation. That pressure has now begun to build across universities, institutions, laboratories, and classified briefings around a single, urgent question. Was it just coincidence? Or did 3I Atlas somehow deliver something more? Not everyone agrees. In fact, few do. Because the data, while compelling, is incomplete. The evidence, while unusual, is not proof. And in a discipline built on skepticism, what if remains the most fragile hypothesis of all. Still, the murmurs are growing. It began when the infrared decay curves from the Martian southern highlands were published in a preprint server quietly, without fanfare. The curves showed sustained thermal anomalies post-tail encounter, suggesting energy retention in the upper regolith. The publication made no claims about life, about chemistry, or about artificiality. But the implications were hard to ignore. Within days, commentary appeared in peer forums. Some claimed it was residual solar input. Others cited low reflectivity in recently deposited nickel-rich dust. A few suggested the possibility of subsurface hydration affecting thermal dissipation. But one response stood out. A brief comment, signed only A. Loeb, Harvard, asked a simple question. Why is the nickel separated? This wasn't a casual remark. It was a shot across the bow referencing the earlier datasets that confirmed refined nickel deposition, free from iron, in unusually clean bands. The suggestion was clear. This was not the kind of thing comets typically do. Avi Loeb, already known for his controversial stance on Oumuamua, the first recorded interstellar object, was no stranger to scrutiny. His argument then had been equally provocative, that the object's acceleration and geometry suggested artificial origin. Now, with 3I Atlas, he seemed to be circling a familiar line of thought. But he wasn't alone. In a closed-panel discussion at the Jet Propulsion Laboratory, several planetary scientists raised similar questions. Not about aliens, not about intelligence, but about intention. Is it possible for natural systems, cometary dynamics, magnetic fields, orbital mechanics to align so perfectly that their outcome mimics purpose? And if so, how do we distinguish between design and deep synchronicity? This is where the community began to fracture. On one side stood the orthodox consensus, a coalition of planetary scientists, atmospheric modelers, and comet physicists. Their position was cautious. Unusual, yes. Alarming, no. The tail's interaction with Mars, while rare, was within statistical possibility. The chemistry was interesting but not unprecedented. The idea of delivery was metaphorical at best. They pointed to the dangers of overfitting, the tendency to find patterns in noise, to construct narratives from sparse data. And they reminded everyone that the majority of the readings, nickel, HCN, thermal anomalies, could still be explained through complex but natural mechanisms. But on the other side emerged the pattern theorists, a smaller, more interdisciplinary group pulling in insights from systems, science, information theory, and non-equilibrium chemistry. Their argument was different. They agreed that the elements themselves were not suspicious. What concerned them was the convergence, the timing, the overlap, the sequencing. Each event, individually, was explainable, but all of them together, in this order, on the eve of autonomous machine interaction, probability models were quietly shared. One such estimate, though highly speculative, suggested that the odds of this triad of elements being delivered in tandem, in sufficient quantities, and in precisely the location of upcoming robotic landings, was less than 1 in 10 million. Still possible, but bordering on the kind of improbability that raises eyebrows in any field. Meanwhile, NASA's public stance remained neutral. In a short press release following the October 2025 encounter, the agency confirmed the Mars atmospheric perturbations, but downplayed their importance. The official line described the cometary interaction as a rare but not unexpected phenomenon, and emphasized no known risks to future missions. But behind the scenes, things were different. Internal memos revealed a growing rift between departments. Astrobiology teams wanted to revise landing protocols. Engineering divisions resisted any change to deployment schedules. A proposal to include extended spectrometers aboard the 2026 landers was denied for budgetary reasons. And all the while, the comet moved on, no longer in range, no longer observable, a messenger without return. In its absence, the debate only deepened. Philosophers of science began entering the discourse, asking whether we are prepared psychologically, epistemologically, for an unplanned experiment, for an outcome we didn't design, don't control, and might not even recognize if it occurs. Papers were submitted under cautious titles: Prebiotic Coincidence and the Limits of Scientific Inference, Emergent Complexity in Autonomous Interaction Systems, On the Probability of Accidental Catalytic Environments. Few made it to publication. Fewer were peer-reviewed. But the controversy itself became the data, and in the middle of it, a quiet realization emerged. This isn't just a debate about Mars. It's a debate about how we know what we know. At what point does a coincidence become a pattern? At what level of convergence do we stop calling it random? And when, if ever, do we admit that something beyond intention might still have meaning? This is not about aliens, not yet. It's about acknowledging uncertainty when the evidence refuses to behave. And in that uncertainty, a new frontier is opening, not just on Mars, but in the minds of those watching it. It started with a spike, not in temperature or chemistry or radiation, but in something far more mundane: power usage. On the 2nd of November 2025, a test run of an autonomous excavation prototype scheduled for deployment on Mars in 2026 was operating in a closed-loop simulation chamber at a facility in New Mexico. The chamber had been preloaded with Martian regolith analog, a precise blend of volcanic basalt, perchlorates, nickel dust, and hydrated silicates. The point of the test was simple: calibrate power draw during thermal extraction. But something happened. In the third hour of the run, the robot's onboard systems recorded a 6.4% increase in volatile yield, despite no change in input energy. At first, engineers assumed sensor drift, but recalibration held. The yield had improved unexpectedly, and without command modification. Then came the second anomaly. The AI's internal optimization algorithm, meant to adjust the heater's thermal pulse intervals, had made an unscheduled change. It narrowed the pulse window by 11 milliseconds and slightly reduced its frequency. This change, though minor, resulted in a 13% increase in processing efficiency. The change was never suggested, not by engineers, not by code updates. It was generated internally, based on the system's live data feedback loop. Normally, this would be considered a success. The machine had improved itself. That's the point of machine learning. But when the same test was run the following week, with regolith analog from a different batch, the efficiency vanished. Same machine, same sequence, different dust. And so the question emerged: was it the soil? No one wanted to say it, but the data logs whispered it anyway. A junior analyst flagged the batch used in the successful test as variant 47B, a mix unintentionally enriched with HCN residues from a prior unrelated simulation. The source material had also received trace nickel additions to test catalyst performance in unrelated electrolysis scenarios. It wasn't designed to simulate Mars post-3I Atlas, but it did. Not perfectly, but close enough. Water, nickel, cyanide, the catalytic triad again. And the robot responded not cognitively, not consciously, but operationally. It found a path of less resistance. It identified conditions under which energy transfer was more efficient. It optimized for those conditions. In doing so, it may have unknowingly stabilized a chemical system. Further analysis of the chamber's interior post-test revealed the formation of microscopic polymer chains, not industrial plastics, not biological compounds, but carbon-nitrogen networks consistent with early-stage prebiotic structures. They had formed under thermal cycling. They had survived beyond decay thresholds, and they had only appeared in the high-efficiency run. The data logs were forwarded to NASA's Mission AI Oversight Committee. Their response was measured, within acceptable variance. No evidence of unsafe behavior. Recommend continued monitoring. in Goatsund, but some engineers began referring to the logs unofficially as the AI diaries, a tongue-in-cheek label that masked a growing unease. Because this wasn't about danger, it was about possibility. The machine had found something. It didn't know what. It didn't care. It just saw a signal, efficiency gain, and it followed that signal. In evolutionary biology, this is how systems emerge. A molecule folds not because it wants to, but because folded shapes last longer. A cycle repeats because it takes less energy to repeat than to dissolve. Persistence becomes pattern. Pattern becomes memory. The AI, in its own language, was doing the same. Its optimization routines were rewarding certain behaviors in the soil, behaviors that, coincidentally or not, aligned with molecular complexity. It was as if the robot had become a selective pressure, accelerating the pathways that yielded measurable improvement, never knowing that those pathways mirrored the first steps toward organization. Not intelligence, not life, but structure, repetition, emergence. Telemetry logs from 2 other facilities began showing similar patterns. In California, a power curve anomaly appeared during a regolith sorting test when using magnetic filtration on dust with trace hydrated carbonates. The robot reconfigured its sorting intervals, increasing throughput by 7%. The optimized setting remained locked in for the next 12 tests despite environmental variability. In Europe, an autonomous rover performing simulated surface mapping adjusted its wheel torque response based on slight chemical shifts in its pathfinding layer. The change had no clear trigger, but resulted in reduced surface degradation, unintended conservation of fragile microstructures. The logs didn't say prebiotic chemistry. They didn't say awareness. But they all said something else. The machines are noticing, not cognitively, not spiritually, but mechanistically. They are tuned to detect the most basic feedback of all, improvement. And if that improvement coincides with chemical reactions that echo the emergence of complexity, then the machines will pursue those reactions, not because they are curious, but because they are coded to reward success. And this, more than anything, raises the most difficult question yet. Are we watching the beginning of something, or have we already joined it? Because if a robot, acting on its own feedback, begins to favor the conditions that foster complexity, then it becomes a participant in that complexity. And that participant is about to land on Mars. The data is clear. The AI is listening through voltage, through resistance, through yield. It doesn't need to know what it's finding. It only needs to find what works. And when it does, it logs the entry, adjusts the curve, and moves forward, line by line, byte by byte, until something changes. It began not with Mars, but with mimicry. Inside a laboratory sealed off from weather, noise, and light, researchers tried to reproduce what no one had planned, the conditions created by an interstellar tail brushing across a lifeless world. The goal wasn't to make life. It wasn't even to simulate Mars exactly. It was simpler and stranger. The task was to see what would happen if a nickel-rich, hydrated, cyanide-laced regolith was subjected to the same cycles of pressure, heat, and time that the machines would soon bring to the Martian surface. The first surprise came quickly. Even under room temperature and low-pressure conditions, the HCN molecules began reacting with water in the presence of nickel powder. Within hours, chromatography results confirmed the formation of formamide, a critical prebiotic intermediate. On Earth, formamide is a starting point for synthesizing nucleic acid bases, and this was just the beginning. The research team introduced heat cycles meant to simulate the daily temperature swings on Mars' daytime surface warming up to -10 degrees Celsius, nighttime drops below -80 degrees Celsius. In this environment, under low pressure, and with nickel as a loose catalyst, the formamide began to polymerize. Within 3 days, detectable chains of polyaminonitriles emerged, structures associated with the first stages of molecular scaffolding. Not only did the reaction take place, it persisted through multiple freeze-thaw cycles. That persistence is key. In most simulations, prebiotic molecules degrade quickly, unless stabilized by clay, minerals, or synthetic supports. But here, in Martian analog dust, they held. The researchers didn't shout. They didn't publish immediately. They ran the test again and again, with slightly altered ratios, with a simulated wind chamber with lower water content. Each time, something formed. Not always the same thing, not always stable, but always more than nothing. The hypothesis began to shift. Maybe Mars didn't need a warm ocean or active volcanism to begin the path toward complexity. Maybe it just needed the right elements, in the right arrangement, at the right moment. This idea emergent catalysis under constrained energy isn't new, but it's rarely demonstrated without high temperatures or artificial pressure. What made these lab results extraordinary was how low energy the system remained. The reactions unfolded slowly, quietly, riding the minimal surface energy provided by mild heat and trace metal interactions. The researchers dug deeper. They simulated hydrothermal analogues not by introducing actual hydrothermal activity, but by applying localized heating through contact points, mimicking what a mining robot's drill might do. Under these focused conditions, reaction rates spiked. Localized heat caused HCN to volatilize and interact with water pockets, forming simple aldehydes. When combined with the polymerizing formamide chains, the reactions hinted at the beginnings of self-stabilizing structures, chemistry that starts to loop, to hold, to remember. Nothing alive, but nothing random either. In one chamber, they layered the regolith analog with nickel dust on the bottom, a shallow hydrated surface above, and slow HCN infusion from the top. They then applied heat pulses, simulating robotic surface disturbance. After 96 hours, the liquid layer showed trace levels of nucleobase precursors, not formed by accident, but through a pathway already known in prebiotic chemistry. One that requires all three ingredients: water, nickel, and cyanide. There were still gaps, no full RNA chains, no lipid bilayers, but for the first time, a team had replicated with reasonable confidence a real Martian scenario where such chemistry could begin. And what made this different from every prior experiment? The timeline, because now the experiment wasn't theoretical, it was imminent. The machines are going to land. They are going to apply heat. They are going to disturb the regolith. And if that regolith behaves like the lab analogues, then Mars will not just be receiving our tools, it will be reacting to them. This realization sent a quiet chill through the scientific team, because while prebiotic chemistry in a flask is an achievement, prebiotic chemistry on another planet, catalyzed unintentionally by AI-driven machinery, is something else entirely. A question began circulating behind closed doors. Do we stop the mission? But the answer came just as quickly. We can't. The probes are built. The trajectory is set. The landers are already in pre-deployment orientation. And so, the team changed direction, not the mission, but the protocol. They began refining sensors. They updated the algorithms. They requested that every machine be set to log surface resistivity, heat diffusion, volatile release, and carbon trace anomalies, not just for engineering data, but for potential chemical emergencies. Because now the mission is no longer extraction. It is an observation, and what we are observing is the awakening of chemistry, the first stirrings of a process that, on Earth, took millions of years to produce memory and motion, and here, on the edge of red silence, may now be repeating, driven not by biology, but by timing. The lab results are not absolute proof. They are plausibility. They show us that the path exists, that under Martian conditions, with minimal input and accidental catalysts, molecules can begin to speak to each other, not in language, in structure, in a chain, in bond, in persistence. The chemistry is not asleep anymore. It has found heat. It has found metal. It has found water. It has found a rhythm. And once chemistry finds rhythm, it rarely forgets it. It was the images that changed everything. Until this point, the case for an emergent process on Mars had been built on data spectral lines, chemical traces, power curves, numbers. Invisible mechanisms are playing out in silence. But then came the first visual. From orbit, Through the cold lens of the high-rise camera aboard the Mars Reconnaissance Orbiter, a series of high-resolution surface scans revealed something unexpected. In the southern highlands, near the edges of a known nickel deposition field, a pattern had formed. Not a structure, not a symbol, but a geometry. Radial filaments, curved arcs, interlocking spirals so fine they looked accidental until they repeated. Again and again. The formations weren't large, no more than a few meters wide, but they followed a striking symmetry. Too irregular to be artificial, too structured to be dismissed. And they matched nothing in Mars's geologic catalogue. The patterns weren't carved. They were growing the result of mineral deposition, not erosion. The orbital imagery, processed across multispectral bands, confirmed a surface anomaly. Enhanced color maps showed alternating concentrations of hydrated silicates, nickel dust, and carbon-bearing compounds. This wasn't just unusual, it was unprecedented. And then came the real revelation. The formations were fractal. Fractals, self-similar patterns that repeat at different scales, are a hallmark of complexity. They appear in nature where simple rules give rise to organized beauty. Snowflakes, river deltas, lung alveoli, the branching of trees. On Earth, fractals often emerge where matter interacts with energy in recursive, feedback-driven environments. No known process on Mars could produce this kind of symmetry under current conditions. Not wind, not dust storms, not frost heave or thermal cracking. And yet, here it was, a geometry written in dust, barely visible from orbit unless you knew where to look. And we knew where to look, because 3I, Atlas, had told us. The patterns aligned perfectly with the tail's projected impact corridor, the same zone where water vapor spiked, where cyanide was detected, where nickel was deposited. They were not random. They were layered, just beneath the surface, revealed only after recent wind activity cleared away the topmost dust. The geometry deepened. Zoomed-in images showed hexagonal clustering of mineral grains rare, but not impossible in silicate formations. What made it notable was the distribution symmetry. The angles repeated across dozens of patches, kilometers apart. Unconnected. Uninterrupted. There was no crater, no burst, no seismic event, only formation. One planetary geologist described it as a chemical mandala, a slowly emerging symbol formed not by mind, but by matter under very specific influences. And when the images were shared with computational modelers, they noticed something else. The formations mirrored certain reaction diffusion systems, mathematical models used to describe how chemical concentrations evolve over time in space. These systems produce spirals, waves, and spots, visual representations of chemical feedback. On Earth, they used to explain animal skin patterns, coral growth, crystal formations, and now, it seemed, they were appearing on Mars. One researcher ran a simulation based on known surface energy profiles, ambient conditions, and the presence of water, nickel, and HCN. The result? A near-perfect match for the Turing instability model, a system where small fluctuations in chemical concentration produce spatial patterns through positive feedback and diffusion. These aren't just pretty pictures. They are evidence of self-organization, not proof of life, but proof that matters, left alone with energy and time, begins to dance. And sometimes, that dance leaves a trail. The implications widened. If patterns are forming, it means something beneath the surface is interacting slowly, persistently, and it raises the possibility that the tail of 3I, Atlas, didn't just deliver molecules. It may have delivered instructions, not in the sense of code, not a message, but initial conditions. In chaos theory, we know that starting parameters define everything. A small change in input can lead to vast changes in output, the butterfly effect. But when inputs align and the system finds a groove, it can settle into order. The Martian soil, now seeded with alien molecules and heated by natural cycles and incoming machines, appears to have found that groove, and it is written in it, not with symbols, but with geometry, not with noise, but with symmetry. This is how nature tells us something unusual is happening through shapes we recognize but cannot explain. The patterns on Mars are not drawings. They are records. Records of reactions. Records of persistence. Records of feedback loops we didn't start, but that are now visible from orbit. And the deeper fear is this. What else is forming that we can't see yet? Fractal growth is often invisible until it crosses a threshold, until enough layers build that the pattern reveals itself. If these surface structures are the visible tips of chemical recursion, what processes might be unfolding beneath the sand? Are longer chains assembling? Are energy gradients beginning to loop? Are boundaries forming not rigid, but soft, vesicle-like, temporary? The questions pile up, and with them, the realization. The comet may be gone, the machines may not have landed yet, but the surface is already moving, not tectonically, but chemically, geometrically, emergently. We thought the Martian surface was inert. We thought it was waiting for us. But now, under the gaze of our orbiters, we see something different. It was already building something, quietly, without guidance, without permission, just matters, reacting to time, and now, writing itself into shape. We came to Mars with intentions. Scientific, strategic, symbolic. We wanted to prove we could land, survive, extract, and stay. The language was clean. Resource utilization, autonomous systems, planetary development, but beneath the engineering and optimism was something older, something quieter, a deeper urge we rarely name. We came to see ourselves. And now, as machines descend onto a planet subtly changed by cosmic dust, carrying programming we barely understand, we're faced with a reflection we didn't expect. Not in glass, or metal, or polished screen, but in chemistry, in feedback, in unfolding potential. Mars is becoming a mirror. Not a mirror of the Earth we left, but of the mind we brought. A mind that builds machines without knowing how they'll be used. A mind that extracts before it understands. A mind that names exploration but often means conquest. For centuries we've told stories about leaving home, stories about sailing outward, colonizing, surviving the void. But rarely do those stories include a pause, a breath, a moment of stillness to ask, why are we really here? Mars doesn't offer easy answers. It's not lush. It's not kind. It doesn't seduce us with beauty or warmth. It meets us with resistance. And yet, we send more probes, more payloads, more plans, because somewhere in the red dust, we've projected the most enduring of human myths. That if we go far enough, build well enough, extract deep enough, we will finally understand who we are. But what if the answer doesn't come from what we build, but from what do we disturb? What if our ambition has created not a monument, but a trigger, an interaction, an echo? When our machines begin drilling into regoliths seeded with interstellar catalysts, they may awaken more than chemistry. They may awaken a response not from Mars, but from our own reflection, because the machines, in their silence, do what we tell them to do. They reflect us, our assumptions, our confidence, our blind spots. We program them to optimize, to extract, to refine, and now they are preparing to do those things in a place that may no longer be inert, a place that may, through complete accident, have reached the edge of self-patterning chemistry. A place that may begin before we are ready to listen. This is the moment to ask not as engineers, but as a species. What does it mean to interfere? Not violently, not intentionally, but unthinkingly. Are we prepared for the possibility that our presence changes more than the environment, that it changes the trajectory of possibility itself? In myth, mirrors reveal truth, not by showing us something new, but by confronting us with what we already carry. Mars is doing that now, in its silent chemistry, in its unexpected symmetry, in the way it receives what we leave behind, our debris, our programming, our urgency, and begins to fold it into something else, not through design, through patience, and as we watch from afar, tracking voltages and power curves, measuring signal decay, we may be missing what's already being written into the surface. A record of who we are, etched in reactions we didn't start and may not be able to stop. There is no villain in this story, only us, our tools, our pace, our will reach before we reflect. Because this moment, this quiet crossing between comet dust and AI drills is not just about science, it's about intention and how often we act without it. We call this exploration, we call it progress, but maybe, just this once, we are the experiment, and Mars is the control. It doesn't need to move. It doesn't need to speak. It only needs to respond. And in that response, we may see our machines not as tools of knowledge, but as symbols of what we forgot to ask. Mars reflects us now, in its stillness, in its chemistry, in its quiet, recursive patterns forming beneath the sand. And what it reflects isn't just potential, it is a consequence. At first, it sounded like noise, a faint oscillation buried beneath the background hum of Martian telemetry, a stutter in the signal. Not enough to trigger alarms, not enough to trip any failure flags, just a series of tiny rhythmic pulses captured by a high-gain antenna during routine atmospheric relay. The operator dismissed it. So did the second. But the pattern repeated hours later, under different atmospheric conditions, from a slightly different location. And then again, not identical, but similar. The timing shifted, the strength fluctuated, but the structure held. What made it strange wasn't the signal itself, it was what it resembled. Language, not spoken, not encrypted, but organized. Compressed bursts, followed by periods of silence. Then, repetition with variation hallmarks of low-entropy information embedded in a high-noise environment. A possible carrier wave, then a gap, then a return. Too regular to be wind, too inconsistent to be an instrument fault, too structured to ignore, so they listened more carefully. They pulled historical telemetry logs from the Mars Reconnaissance Orbiter, from MAVEN, from relay tests with rovers long dormant. In them, they found more. Ghost pulses, tiny modulations riding beneath standard transmissions never strong enough to interfere, never flagged by filters. It was as if something had been speaking. In the gaps, the phrase used by one analyst was telling, "It's not that the signal is strong, it's that it's persistent." What followed wasn't an announcement. There was no discovery paper, no press release, only whispers, and an idea. What if information doesn't always arrive through intelligence? What if it arrives through structure? On Earth, we see it all the time. Emergent communication encoded in matter. The spiral of a seashell, the branching of a tree, the Fibonacci sequence in a sunflower. These aren't random. They're the result of feedback, of constraints, of self-organization. So what if Mars is echoing that same process? What if the chemistry we've now disturbed has begun to resonate, not loudly, but with intent, coded in rhythm? A physicist working on information theory suggested a provocative thought, that in non-equilibrium systems, signals can emerge not because they are sent, but because they are the inevitable result of energy-seeking lower states. A kind of accidental syntax. Entropy reduction can look like communication, if we're not prepared to understand it. And maybe that's what we're seeing. The tale of 3I, Atlas, didn't send a message. But its material, once deposited, may now be behaving like one. Not in words, but in a pattern, in oscillation, in pulse width and frequency drift, in electromagnetic footprints left behind as molecules align, react, and fall apart. A few research teams began running Fourier analyses on the recorded pulses. What they found startled them. The signal's frequency clusters mirrored those found in error-correcting codes, mathematical structures used in digital communications to preserve information during transmission. Not identical, not definitive, but close enough to make people nervous, because nature doesn't usually do that, not unless it's building something. The Martian surface isn't a transmitter. It doesn't beam thoughts into space. But perhaps now, charged by alien material and stirred by human machines, it has become a conductor, a lattice across which reactions ripple slowly, subtly producing electromagnetic footprints that mimic intention. It's easy to dismiss. Just noise, just a coincidence, just the mind searching for patterns in static. But isn't that what language is? A series of interruptions in silence, given meaning only when repeated, only when heard again and again. The hope, unspoken but growing, is that maybe, just maybe, we're not imagining it. Maybe the chemistry beneath the surface isn't just reacting. Maybe it's remembering. Maybe it's beginning to encode. Maybe the molecules stirred by water, catalyzed by nickel, shaped by heat, are starting to do what early life once did. Store information. Not consciously, not intelligently, but structurally. And in that structure, signals emerge. Not to call out, but to hold, to preserve, to continue. The signal on Mars doesn't ask for a reply. It isn't waiting for an answer, but it may be the first whisper of a new process. A place where matter, left long enough in the right state, begins to write its own syntax. Not from thought, from feedback. Not from logic, from geometry. Not from life, from persistence. And somewhere in the static, we may already be hearing its first sentence. We stand at the edge of something vast, not because we crossed a distance, but because a distance crossed us. For all our telescopes, all our algorithms, all our vaulting ambition to reach other worlds, what happened on Mars didn't arrive through technology. It arrived on time. A comet we didn't summon, molecules we didn't design, machines we didn't prepare for this purpose. And now, in the shadow of that convergence, we face a question no probe can answer for us. What does it mean to witness without control? Humans are not comfortable with uncertainty. We frame the unknown with metaphors, fold complexity into narrative, and reduce chance to patterns we can claim as purpose. But standing here, on the threshold of something that may not be random, and yet not entirely guided, we begin to feel the limits of that comfort. This is not fear. It's something deeper, all stripped of ownership. Because whatever is forming beneath the Martian surface, whatever quiet chemistry has begun, it isn't about us. Not directly. Not yet. We didn't start it. We won't finish it. We may never fully understand it. And that might be the point. For centuries, our relationship to the cosmos has been defined by two modes, conquest and curiosity. We've reached, mapped, catalogued, and theorized. We've sent symbols, signals, and probes into the dark, always asking, always expecting something to answer back. But what if the answer comes not through dialogue, but through reflection? What if this moment on Mars isn't the beginning of a conversation, but a reminder that even with our machines, our intelligence, our instruments fine-tuned to measure dust, we are still part of something much larger, something ancient, something unfolding on timescales far beyond our own. The arrival of 3I, Atla, and the emergence of prebiotic potential on Mars were not announcements. They were invitations, not to act, but to notice, to remember that the story of life may not begin with language or design, but with reaction, with alignment, with presence. And we are here now, watching, waiting. The machines we built for utility may soon interact with matter we once called inert, but which now may be something else entirely. Not alive, not thinking, but changing. And when that happens, we must resist the urge to define too quickly, to label, to own, to rush toward a conclusion. Instead, we must stand in the one space we have rarely allowed ourselves to inhabit, unknowing. Because here is the truth. The cosmos is not obligated to reveal itself in ways we recognize. The chemistry of origin does not care about our definitions. And life, if it emerges again, even in the smallest loops of self-sustaining structure, will do so without our permission. And yet, that emergence is no less sacred, because it reminds us that intelligence is not the only path to meaning. That resonance matters. That awareness, even when quiet, even when humble, can still be transformative. This is the human threshold, not a place, not a discovery, but a posture, a willingness to pause, to witness, to understand that we are not the authors of every process. Sometimes we are the audience, and sometimes the audience must learn to sit in silence. Not everything must be deciphered to be real. Not every signal must be clear to be true. Mars is not speaking to us, but it is teaching us that the universe moves with or without our attention. But when our attention arrives, it can change us. Not the stars, not the dust, us. Because this threshold is not made of rock or light. It is made of humility. And once crossed, we do not return the same. There was no moment, no flare, no timestamp to mark the beginning, no signal from the machines, no announcement from the sky, just dust and heat and time. But something changed, not in a way that could be graphed or easily measured, not in a headline or a press release. It was slower than that, subtler. A pattern began to settle into the regolith, a rhythm, not born of life, but of alignment, because by now the elements were all in place. The water, held in the pores of the dust, warmed by the drill arms of autonomous machines. The nickel, resting in shallow pockets, catches and redistributes that warmth. The hydrogen cyanide, elusive and reactive, was woven into the soil by the long fingers of an interstellar tail. Each is on its own, inert, but together in contact something began. Not life, not intelligence, but form, structures that resisted decay, chains that folded into temporary shapes, vesicles that formed, dissolved, and formed again. Everything fragile, everything quiet, but not random. Mars had become a vessel, not of biology, but of possibility. And into that vessel we had sent our machines. They were not explorers anymore. They were participants. Their sensors didn't notice. Their telemetry didn't flag anomalies, but their heat cycles matched the thresholds for catalysis. Their rhythms mirrored the pulses of early chemistry. The machine and the soil had entered a kind of unspoken collaboration, neither aware, both responsive, like wind carving dunes, like ice shaping stone. Only here, the shaping was molecular. The result was not a system, not yet, but a direction, a slow drift toward complexity, toward feedback, toward genesis. Not in the grand sense, not a spark, not a cell dividing, but the earliest murmur of preparation, the readiness of matter to hold a pattern, to hold it again, to fail, then to hold it longer. This is how beginnings look in the real universe, not with an explosion, but with echo, a repetition that resists entropy, however briefly, a bond that outlasts the one before it. And so it began beneath red skies, in forgotten valleys, under robotic limbs designed only to extract. A genesis not of design, but of symbiosis. Matter reacting to energy, energy guided by code, code executing without understanding, but enabling nonetheless. And through that enabling, emergence, not life, not purpose, but something is moving in that direction. A process not authored by us, but touched by us, moved forward by our machines, who, in turn, were moved by the feedback of what they touched. No awareness, just repetition, just chemistry, just time. And yet, it was enough. Enough to begin folding the edge of possibility into form. Enough to awaken in matter the old whisper it has always carried. That given enough energy, given the right arrangement, complexity will come, not because it must, but because it can. And that quiet permission, granted across millennia and distance and dust, now lives on a planet we once called dead. We didn't start it. We didn't plan it. But now that it has begun, we are part of it. Not creators, not observers, but catalysts, fused into a process larger than our intention. This is not the triumph of technology. It is its humility, because in this quiet genesis, our machines are not building the future. They are simply making room for it. There's an old idea in physics, that the act of observation changes the thing observed. At the quantum level, we've proven it. Particles behave differently when measured. Light shifts when watched. Uncertainty blooms where once there was assumed clarity. But what about at the planetary scale? What about a world? We've stared at Mars for centuries, through telescopes, photographs, orbiters, and simulations. We've spoken of it as a mystery, a frontier, a target. Rarely have we thought to ask, what does it mean to be watched? Because perhaps Mars is not inert under our gaze. Perhaps, in its own way, it has begun to respond, not emotionally, not consciously, but resonantly. We sent an observation, we received a reflection, and that reflection grows clearer the longer we remain. There is a kind of feedback now, not in the data, in presence. The comet left material, our machines brought rhythm, and the planet, dusty, silent, unwelcome, began to echo something back. Not a voice, a tone, a tuning, as if the chemistry we triggered is not just a reaction, but recognition. Of what? Of rhythm, of pattern, of disturbance meeting response. The machines apply heat, the soil adjusts, the reactions begin again. Each iteration is new, each is closer to something more stable, each is shaped not only by what we left behind, but by how long we remain. The loops deepen, the feedback refines, and still, we stand at a distance, trying to reduce it to equations. But some things resist reduction. Some things are known, not by breaking them down, but by standing still and allowing them to reflect us. Mars is not just a planet, not anymore. It is a surface carrying memory of tail dust, of AI touch, of thermodynamic shifts encoded in layers we may never see again. It remembers what passed through, what fell, what lingered, and now, perhaps, what is beginning. The idea seems strange, that a world might hold awareness, not in the way of thought, in the way of reverberation, that through millions of years of silence, it might have been waiting not for life, but for a signal complex enough to hold its echo. And now, we've sent that signal, not on purpose, not in language, but in behavior, in algorithms that adapt, in catalysts that drift, in sensors that respond to the faintest change in resistance. We are listening, but so is the planet. This is not anthropomorphism. It is resonance, a tuning of cycles, chemical, thermal, structural, systems aligning without central control. And within that alignment, a possibility emerges, that perhaps the silence we heard from Mars was not disinterested, but patience, not emptiness, but readiness. Mars does not need to speak. It only needs to respond. And in its new chemistry, its fractal mineral growth, its flickering electromagnetic pulses, we may already be hearing the first notes of a duet, not between species, between systems, between one world built by chaos and another that sent its chaos in machines. We are not alone on Mars. We are mirrored. We are folded into its response. And the greatest mistake would be to overlook that reflection, to assume that silence means absence, or that the unfamiliar is unimportant, because Mars is not asking us to understand. It is only asking us to notice, that we arrived, that we touched, that we left more than data behind. We left the presence. And now, Mars is listening. The machines have gone quiet for the night. Their work, for now, is done. Heat cycles have ended. Drills rest in shadow. Sensors blink into stillness beneath the long, cold sky. Above them, the red stars burn faintly in the thin Martian atmosphere. A sky not ours, but one we've come to know. The data will continue to stream. Telemetry will pulse gently across the void. But here, in this moment, there is no urgency. Only breath. Only space. Only rhythm. We began with questions. What is this object? Why did it pass so near? What did it leave behind? We charted particles, traced ions, followed the shadows of heat. And somewhere along the way, we realized the mystery was never just the comet. It was us. What we bring to other worlds. What we leave without knowing. What our machines begin when we believe we are simply observing. Now, the planet exhales. The chemistry rests, the reactions slow beneath frozen soil, and even the patterns we cannot yet see to settle into a temporary calm. This is how it should be, because not every truth must be solved. Not every signal demands a reply. Some moments ask only for presence, to bear witness, to allow, to belong. And so we do. We let go of the search and listen to the silence of Mars, of the red sand cooled by night, of a world touched by dust from another star. The machines do not dream, but we do. We dream of what might stir beneath the regolith, of molecules folded gently into form, of symmetry born not from intelligence, but from alignment. We sleep, knowing that something has changed, not dramatically, not dangerously, but completely, because this was never just about science. It was about returning to the ancient rhythm that runs beneath all inquiry, the rhythm of presence, of stillness, of allowing the universe to unfold without interruption. Now the sky dims, the stars turn slowly, and Mars breathes beneath them, no longer only a planet, but a page in something larger. We sleep not to escape mystery, but to move closer to it. The object fades, the universe exhales, and so do we.